Welcome back. Today we're looking at a paper that really caught my eye. VAR done right, tackling asynchronous policy conflicts in visual autoregressive generation from Sun et al. At Tsinghua University and ByteDance. So if you ever tried to use reinforcement learning to align one of these big course-defined visual autoregressive models of VAR, it can be a total disaster. The core problem this paper tackles is something they call asynchronous policy conflicts, which basically just crashes the whole training process.
And their solution is this really brilliant three-part framework. It's designed to fix group relative policy optimization, or GRPO, specifically for these VAR models.
Let's break it down. First, there's value as middle return, or VMR. It stabilizes training by splitting the objective into two stages. Second, per action normalization weighting, PANW, which balances out the gradients across different resolutions.
And third, Mask Propagation, or MP, which is all about focusing the credit assignment only on the tokens that actually matter for the final reward.
And the results are just huge. For text rendering, they got a 41.6% relative improvement in word accuracy.
A massive jump. And on top of that, they hit state-of-the-art on the HPSV3 human preference score, even against strong diffusion models. It's a real game changer.
Okay, so to really get why that 41% gain is so significant, we need to dig into the architectural headache that VARs represent. We've got three main paradigms for visual generation right now, right? Autoregressive, diffusion, and these VARs.
Exactly. And AR models are, one token at a time sequential. Diffusion models mostly work in a fixed latent space. But VARs are totally different because they generate course define. They paint the big picture first, then fill in the details.
And the key detail, the thing that causes all the trouble, is that at each step of this refinement process, the model spits out a parallel grid of tokens. And the size of that grid times WD-bar changes, sometimes dramatically, as you go up in resolution.
That's it. That's the birthplace of the asynchronous policy conflict. The number of query tokens you're dealing with can fluctuate by orders of magnitude. You go from a tiny grid to a massive one.
Let's pause on that for a second. What makes that fluctuating token count so much more catastrophic here? I mean, other models deal with sequences of different lengths.
It's a great question. The problem is really two things. First, those early course-level decisions are foundational. They set the entire structure of the final image. And second, the sheer scale of the fluctuation creates this huge variance in what the paper calls task similarity.
Okay, can you break that down a bit?
Sure.
Yeah.
Think of it like this. In the first few steps, you're making, say, 10 big decisions about the overall composition. In the last few steps, you're making thousands of tiny decisions about pixel-level texture.
Right.
If you just use one final reward signal for the whole process, the gradient from those thousands of tiny texture decisions completely overwhelms the signal from the 10 important compositional ones. The model starts optimizing for noise, and the whole structure becomes unstable.
And this is made worse because the RL fine-tuning stage uses way fewer samples than the initial pre-training, right? You have less data to average out that noise.
Precisely. And they prove this point in the paper. When they tried a vanilla GRPO approach across the whole sequence, it actually performed worse than just training the first few stages and ignoring the high-resolution parts completely.
So doing the full optimization was actively hurting performance.
It was. So the authors knew they couldn't just throw a standard RL algorithm at it. They had to formalize the whole VAR generation process as a deterministic Markov decision process, an MDP, to really understand the dynamics.
Which brings us to their first and maybe most important component, value as middle return, or VMR. This is the big structural fix.
It is. It's designed to break up that long, noisy reward horizon into two much more stable pieces.
So how does that decomposition actually work? Are they just inventing a new reward halfway through?
They are, but it's done in a very principled way. The idea is to split the whole optimization problem at some middle time step. Let's call it to $1. This gives you a prefix task, everything up to step $1, and a suffix task, everything after.
The suffix task sounds straightforward. You're just trying to maximize the final reward, 3ST.
Correct. The real innovation is in the prefix task. Instead of asking those early steps to predict a noisy, distant final reward, you ask them to maximize the expected middle step soft value. Basically a prediction of how good the image should be at that halfway point.
I see. So you're giving the early structural decisions a closer, cleaner, lower variance target to aim for.
Exactly. It stops those cross-horizon conflicts where a decision at step 1 has this tiny, noisy effect on the reward 10 steps later.
But hold on, if you introduce a new intermediate value, how do you know you aren't just finding an easier but suboptimal solution? How do you guarantee you're still aiming for the best possible final image?
That's the critical question. And they answer it with their theorem 2, the two-stage invariance theorem. They prove that VMR is what's called a structure-preserving reward shaping technique.
Meaning
Meaning that introducing this middle value function does not change the optimal policy. You get all the stability benefits without sacrificing the true global objective. It's the difference between a clever hack and a real principled solution.
that's incredibly elegant. So did they have to train a whole separate value network for this? That sounds expensive.
Fortunately, no. They estimate VMR directly from the on-policy terminal rewards using a risk-sensitive estimator. They found that just a couple of samples, Kashima-2 dolls, was enough to get a stable estimate without all the overhead.
And where did they find the sweet spot for that split for over $? Was it better to split early or late?
Definitely earlier. Their ablations showed the best results came when Y in dollars was to the 128 by 128 or 256 by 256 resolution mark. They ended up using 256 as the default since it gave great quality with less compute cost for the estimation.
And what happened if they pushed it later, say, to the 512 resolution?
Performance dropped off, which just reinforces their main point. The biggest conflicts are happening in those early prefix stages. If you can stabilize those structural decisions, the rest of the generation is much more robust.
Okay, so VMR fixes the problem over time. It's the temporal fix. But we still have that issue of scale, right? The massive number of tokens in the later stages. How do they stop those from just drowning out the gradients?
That's a perfect transition to the second component, per action normalization weighting, or PANW. This directly tackles that gradient imbalance we were talking about.
It's the tyranny of the majority, where the sheer volume of high-res tokens dictates the policy.
Exactly. PANW is a simple but effective fix. It just weights the loss at each step by a normalization factor. The core idea is if a step generates, say, 1,000 tokens, its contribution to the final gradient gets scaled down, so it doesn't just bulldoze the policy updates from a step that only generated 10 tokens.
It sounds like you're basically normalizing the learning rate across different scales. What did they find when they tuned that decay exponent, alpha?
They found a real sweet spot between 0.6 and 0.8. If alpha was 0, you get no normalization and the instability comes right back. But if it was too high, you risk suppressing the high-resolution details too much. You need those for a sharp image, after all.
So you need to turn down the volume on the later stages, but not mute them completely.
A perfect analogy.
Okay, so VMR for the temporal objective, PANW for the gradient scale. The last piece is mask propagation, MP, which seems to be about sharpening the focus of the updates.
Right. MP is all about efficient credit assignment. You need to make sure you're only updating the parts of the model that actually contributed to the reward. This is super important for a task like text rendering, where your reward is coming from a very specific part of the image, like a bounding box.
So how does this mask actually work?
It's pretty clever. When they calculate the final reward, they create an initial mask over the pixels that determine that reward, say, the pixels inside the rendered text bounding box. Then they propagate that mask backwards through the model's layers, from the finest resolution all the way back to the coarsest. It's like an X-ray that highlights only the regions and tokens that had a causal influence on that final score.
And only those highlighted tokens get the gradient update.
You got it. It dramatically reduces variance, both spatially and temporally. You stop wasting updates on parts of the image that had nothing to do with the text you were trying to render. And the ablations show this works-enabling MP gave a significant boost to all their text fidelity metrics.
So the three components really work together. VMR fixes the when, PANW fixes the how much, and MP fixes the where. Let's see how this all translated into actual performance, starting with that text rendering task.
Yeah, text rendering is a brutal stress test.
Yeah.
Any small error, like a swap letter or a weird-looking character, is immediately obvious and just ruins the image. They use the NextFlow model as their base.
And that reward function they designed was incredibly complex. It wasn't just a simple accuracy score.
No, it had to be. They used PADL-OCR and combined three things. First, a confidence-aware completeness score to make sure all characters are there. Second, a length mismatch penalty to punish the model for adding or removing characters.
So it's not enough to get the letters right. You need the right number of the right letters.
Absolutely. And third, a confidence-weighted similarity score based on Levenshtein distance to make sure the sequence itself is correct. It's a very carefully engineered reward.
And the results with this framework?
They were just transformative. Word accuracy went from about 0.55 to 0.78. That's the 41.6% relative gain. Normalized edit distance, another key metric, also saw a huge jump.
And you can see it in the images. It's the difference between garbled, messy text and crisp, clean, correct rendering. It really shows their method solves the core problem.
And it wasn't just for text. To prove it generalized, they also optimized the model directly for the Human Preference Score, or HPSV3.
So training the model just to make images that people find aesthetically pleasing.
Exactly. And again, big gains. The overall HPS score jumped by over 2 full points from 8.43 to 10.64. And in the papers tables, you can see NextFlow-RL becomes state-of-the-art among similar models in a bunch of categories: architecture, animals, scenery, you name it.
That's a powerful point. It means fixing this core instability doesn't just make the model better at one specific task. It makes it fundamentally better at generating coherent, high-quality images that people actually like.
The structural integrity you get from VMR and PANW just improves everything downstream.
Before we wrap up, there was one last ablation on the training schedule that I thought was interesting. It was about how they alternated between updating the prefix and suffix parts of the model.
Oh, right. They compared a coarse alternation, like one for one, with a more fine-grained approach.
And the fine-grained approach was better.
Much better. The best results came from doing 3 prefix updates for every 1 suffix update. It just hammers home the point that you have to give constant focused attention to those early structural stages. If you don't solve the policy conflicts there, quickly and often, the whole thing falls apart.
This whole paper really feels like a masterclass in how to apply RL to these complex architectures. You can't just use an off-the-shelf algorithm. You have to design the solution around the model's specific quirks.
It's the first truly systematic approach to RL for VARs in text-to-image, and it proves that with the right objective structure and gradient control, you can solve these asynchronous policy conflicts. That 41.6% accuracy gain is the proof.
An incredibly elegant solution that fixes the problem at its root.
And it leaves us with a really interesting question for what comes next. The whole success of VMR, specifically that invariance proof, relies on the VAR generation being a deterministic process. But what happens when you extend these models to things like video or 3D generation, where the world isn't so predictable? Can we develop similar structure-preserving techniques that are proven to work when the environment itself is stochastic? Solving that could unlock reliable RL for the next generation of generative models.